Hi everyone, my name is Ayman Fooli, and I have created this channel specifically for anyone who wants to learn about ELS software or extreme loading for structures software. This channel is specifically for all the users and all the engineers who has questions about ELS and how it works, how easy is the modeling, how easy is applying the loads, and so on. Let's first begin with this chart. This chart is showing what we call the structure behavior from birth to death. Here in this chart, we will learn about the advantages of using ELS software in doing nonlinear structural analysis. So this chart is showing what we call structure behavior from birth to death. Birth when the structure is being constructed, up to this when you have an extreme event that happened to your building that leads to either a partial collapse or a total collapse for your building. So there are two behaviors for the material. The first behavior is a quantum behavior where the material in the beginning begin to work in the linear stage, in the linear elastic stage. Then it goes to cracking, yielding, and crushing, and also buckling and post buckling. Then the material goes to the discrete behavior where elements start to separate from each other, leading to debris falling as rigid bodies and then collision between those elements and then the collision with the ground. So there are many numerical analysis methods available in the market. The first one that we all know about it, which is the FEM method, it's very good when it comes to linear elastic analysis. Then when you go to cracking and yielding and crushing, also buckling and post buckling, the user has to put some assumptions in his model, especially if you are using something like SAP 2000 or ETABS or Perform 3D or any simplified nonlinear analysis software. For example, you put the end offsets and its rigidity. You also have to assign the locations of the plastic hinges. And finally, you have to account for the rigidity of the connections. When the material goes to element separation and debris and collision, this cannot be automated in the simplified nonlinear analysis methods. However, it can be done if you are using something like ANSYS or LS-DYNA or any advanced high-fidelity numerical modeling tool, but the user also has to predefine the cracking location and the element sizes to allow for something that we call element erosion technique, where the element is being removed from the analysis completely. There are also the discrete element method. It's very good when it comes to element separation, debris folding, and collision. However, it has some problems when you are dealing with static analysis or doing the quantum material behavior like the cracking and the linear elastic analysis as well as the buckling. That's why there is now a new numerical analysis method. It is actually not very new. It is called the Applied Element Method, AEM, where it covers the whole history of the material behavior, starting from the linear stage to cracking, buckling, element separation, and debris and collision. All of these is automated inside the technology that we are going to use. Let's see an example in here. So in this example, we are showing the Champlain Tower that collapsed in Miami, Florida, a year and a half ago. So in this example, we remove some towers from the water table and we clean the water and we start to see the cracking and the separation of the towers, followed by the failure in this part from the material as we can see. So let's now speak about the applied element method. What is the applied element method? The applied element method, it is a stiffness-based method similar to FEM, where we discretize each structural components like columns, beams, slabs, and so on into several solid elements, and then we connect those elements together with what we call material springs. The material springs represents the axial deformations as well as the shear deformations that happens inside the material. Let's have an example in here. So if we have an RC column like this, we have two materials inside this column, the concrete material and also the reinforcement rebar inside this component. So we discretize, as we said, the structure component into several elements as we see in here. And then let's take a look on element number one and element number two. Element number one here and element number two, what we do is that we generate at the interfaces between the springs two types or three types of springs. Basically, the springs that are generated 5 by 5 spring, and each spring of these represents the normal deformations and the shear deformations that happen inside the material. So one normal spring for the normal deformations and two shear springs for the shear deformations, one in XZ direction and one in YZ direction. With the same exact concept, if we are talking about the reinforcement bars, so let's assume that we have a reinforcement rebar that's going to pass between those two elements in here. So here is the reinforcement rebar. We replace the reinforcement rebar at its exact location again with one normal spring and two shear springs, one in XZ direction and one in YZ direction, as we have seen in here. There are some differences between the applied element method and the finite element method. For example, the first difference between them is that in the finite element method, if you are applying a tension load on this member in here, so we see that the elements here or the element deforms. However, the nodes cannot be separated from each other. Here in the applied element method, the element itself is rigid, so no deformations is happening inside the elements. All the deformations are happening at the interfaces between the elements as we can see in here. So if you are applying here a tension load, let's say of 1 inch, then the total displacement here is going to be 1 inch. Also here in the applied element method, the total displacement is going to be 1 inch. One other difference is in the degrees of the freedom. So if you are using something like ANSYS or LS Dyna or Abacus and you are using an 8 node element or brick element or a solid element with 8 nodes, then you have 3 degrees of the freedom at each node. Basically, you have for each element 24 degrees of the freedom. Here in the applied element method, the degrees of the freedom is in the CG of the elements. So we have only 6 degrees of the freedom. 3 for the translation, as we can see in here, and 3 for the rotation, as we can see in here. And this actually makes the solver of the applied element method much more faster than any FEM solver working with a solid element modeling. One also difference is in the connectivity between the elements. Here in the finite element method, if you have two members that meet at a face like this, like a partial a meeting point, as we can see in here, or meeting surface, then you have a problem here in the finite element method because you have to have nodal compatibility. In the applied element method, this is not a problem because any elements that face another element, even if it was a partial overlap between them, springs and connectivity is going to be generated here automatically. And this actually makes the meshing much more effective if you are using the applied element method than the finite element method. For example, if you have an area here of a coarse meshing and area of a fine meshing in the finite element, then you have to have a transition zone in between them. In the applied element method, this is not a problem. Any big element that's going to connect to another smaller elements, as we said before, springs are going to be generated here automatically. And of course, you can choose whatever kind of material that's going to be generated at this interface between the two components. All our material models that we are using are nonlinear material models. For example, this is the material model that we use for the concrete, and it is a fully path dependent model. Also, this one is used for the steel, and again, it is a fully path dependent model. Also, we have the ability to import user defined material models. So, if you have your own material model and you wish to import it inside ELS, all what you have to do is to import the stress and strain relation for this material and then define whatever failure criteria you are going to use. Either it is von Mises or more column or basically a stress limit. Finally, this is what you get when you are doing finite element analysis for a collapse case. Everything behaves like rubber because elements cannot be separated from each other. While this, what you can see here, if you are using the applied element method or extreme loading for structures software. Thank you and see you next time.